On April 17th, 54 tornadoes tore across the American Midwest in a single afternoon. 2 of them, rated EF3, erased entire neighborhoods in Wisconsin in under 90 seconds. And here is the part that should make the hair on the back of your neck stand up. None of it was random. Every storm, every siren, every shattered home landed exactly where a peer-reviewed study from 2015 said it would. The atmosphere is reading from a script, and Thursday this week, it will turn the page, loading up a single weather system that is about to unleash tornadoes, blizzards, wildfires and floods on the same day. And all of this, every bit of it, is happening before El Niño has even officially arrived. Stay with me, because if this is the warm-up, what happens when the main event begins? If this has you hooked, hit like and subscribe to the Skylab, because you're going to want to be here when the next batch of data comes in. Drop a comment below. I genuinely want to know where in the world you're watching this from, what time it is there, and your honest answer to this. If the atmosphere is already following a 2015 scientific playbook step by step, producing 54 tornadoes in a single afternoon and quad-hazard weather events on a 6 to 8 day schedule, all before El Niño has officially arrived, how much worse do you think this gets when the Pacific fully commits? Let me know what you think. Now, let's get into it. Part 1. This wasn't random, it was scheduled. On April 17th, the sky over the American Midwest did something that most people assumed was just bad luck. 54 tornado reports poured in across a single afternoon and evening. 28 of them were later confirmed as actual tornadoes on the ground. 2 of those were rated EF3, which puts them in the top 2 to 3% of all tornadoes that ever touch the Earth in a given year. Winds inside those 2 storms exceeded 136 miles per hour. Entire neighborhoods in Ringgold, Wisconsin and across Marathon County were reduced to splinters and insulation. Homes that had stood for generations were gone in under 90 seconds, cars were thrown. Trees that had been rooted since before the Second World War were snapped at the base like dry pencils. And here is the part that really makes you stop and reread the numbers. Across that same 24-hour window, the Storm Prediction Center logged around 750 total severe weather reports. 300 plus severe thunderstorm warnings were issued. 150 plus tornado warnings screamed out of phones, televisions and weather radios. If you stacked those numbers against a normal April day, you would not find a comparison. You would find a blank space where a comparison is supposed to live. And yet, despite all of that, the casualty count was shockingly low. That is not a detail to skip over. When a system of that magnitude moves through that much populated terrain and leaves neighborhoods flattened, you expect a body count. The fact that the warning systems performed almost flawlessly, that people took shelter, that forecasters had the storms nailed down hours in advance, tells you something very specific. It tells you that the atmosphere on April 17th was not behaving randomly. It was behaving so predictably that the professionals watching it could see it coming like headlights on a long, dark road. And that is the thread I want you to hold on to for the rest of this video, because everything we're about to unpack hangs from it. The 2026 tornado season is not chaotic. It is not lawless. It is not the atmosphere throwing a tantrum. It is a highly structured El Niño Southern Oscillation-driven pattern, and it is behaving almost exactly the way a peer-reviewed study predicted it would behave more than a decade ago. The real question, the one that should be keeping meteorologists up at night, is not what happened on April 17th. It is what happens when the forcing behind this pattern gets stronger. Now, 6 days later, the atmosphere is already reloading, and I want you to sit with that phrasing for a second because it matters. Reloading, not resetting, not calming down, not catching its breath. The same machinery that produced the April 17th outbreak is spinning back up for another run, and the Storm Prediction Center has been telegraphing it for days. A 15% risk area has been drawn across the plains and Midwest for April 23rd, and that risk area is not a wild guess. It is the output of models that are watching the exact same atmospheric configuration reassemble itself over the Rockies, like a stage crew resetting the props between acts. So what does that mean? It means that whatever produced the April 17th outbreak did not leave. It just took a breath. The ingredients, the moisture, the wind shear, the instability, the jet stream positioning, the upper level trough, all of it is reconstituting. Same recipe, same kitchen, same cook. And that is why, when I tell you this is not isolated severe weather, I am not being dramatic. I am being precise. This is a repeating atmospheric configuration, and when you see something repeat with this kind of fidelity, you stop calling it weather and you start calling it a pattern. Let me put it this way. A normal tornado season is messy. It is a series of loosely connected events that come and go with no particular rhythm. 1 week you get an outbreak in Oklahoma. 3 weeks later you get one in Mississippi. A month after that you get nothing at all. The ingredients come together by accident, and when they do you get storms. When they do not, you get a quiet Tuesday. That is how April is supposed to look. Chaotic, inconsistent, difficult to forecast more than a few days out. 2026 does not look like that. 2026 looks structured. The outbreaks are arriving on a schedule. The geography is staying consistent. The ingredients are showing up on cue. The severe weather parameters are repeating themselves with almost eerie similarity from one event to the next. And when you lay it all out on a calendar and a map, you start to see something that does not feel like a weather season at all. It feels like a system that is being driven. And that is where the unease creeps in. Because if this season is predictable, if it is following a rule book, if the atmosphere is doing exactly what theory says it should do given the state of the Pacific Ocean, then the April 17th outbreak was not a surprise. It was a confirmation. And the April 23rd event that is loading up right now is not a coincidence either. It is the next line in a script that was written years ago and is now being read aloud in real time. So here is the question I want you to carry with you into the next section. If this pattern is this predictable, this early in the season, with the Pacific only drifting toward full El Niño conditions, what does that imply about the outbreaks that are still to come? Because if the atmosphere is already behaving like this on what amounts to a warm-up run, then the main event whenever it arrives is going to be something we need to take very, very seriously. And the clue to what is coming next is not in the storms themselves. It is in what the system did after the storms ended, because it did not actually end. Part 2, the system didn't end, it's still running. Most people think of a tornado outbreak as a discrete event. It arrives, it does its damage, and then it leaves. The sun comes out the next morning, the cleanup crews move in, and the atmosphere moves on to whatever it is doing next. That is the mental model most of us carry around, and for most tornado seasons in most years, it is a reasonable one, but not this one. The April 17th system did not actually end. Days later, its fingerprints are still all over the landscape, and the atmosphere that produced it has refused to do what a normal atmosphere is supposed to do after a major outbreak. It has refused to reset. The rivers are still telling the story. Flood warnings remain active across large swathes of Wisconsin and Kansas, because the rain that came down with the tornadoes did not all run off in a single afternoon. It is still working its way through the drainage system, still rising in places, still threatening towns that thought the worst was over when the funnel clouds lifted. And that is not a detail you usually see after a spring outbreak. Usually the hydrological signature fades within a day or two. This one is not fading. It is lingering. And it is lingering because the atmosphere that dumped all that water is not moving on. This is what I mean when I say the atmosphere is not resetting. In a normal year, after a major severe weather event, you get a stretch of quieter days. The ridge builds back in, the jet stream relaxes, the ingredients separate, and the system has time to reload from scratch before the next round. That is the natural rhythm of spring weather in the central United States. Storm, quiet. Storm, quiet. Like a heartbeat with a long diastolic pause. 2026 does not have that pause. The diastole is missing. The systems are overlapping instead of dissipating, and that changes everything about how you read what is happening. And while the flood warnings are still active, something else is happening on top of them that, if you only half-watch the forecast, you might have missed entirely. A wall of cold air is carving down across the central and eastern United States, with temperature drops of 15 to 30 degrees Fahrenheit slamming into regions that just a few days ago were hitting highs in the 70s and 80s. That is not a normal transition. That is a hammer blow. Crops that broke dormancy during the warm stretch are now staring down a freeze threat, and farmers across the Midwest and Mid-Atlantic are doing the calculus on how much of their early growth is going to survive. And even that is not the end of it. Late-season snow is now on the table for parts of the Northeast, including the Adirondacks and sections of New England that were already well past their last frost dates on paper. We are talking about the kind of anomaly where residents look out the window in late April, and see flakes coming down on grass that was green yesterday. Snow in late April is not unheard of in those regions, but the timing of it, stacked on top of the tornado outbreak, stacked on top of the flooding, stacked on top of the cold intrusion, forms a pattern that you cannot explain by calling it normal spring variability. Because here is what is actually happening. This is not a series of separate weather events. This is one multi-phase system behaving like a single organism with multiple limbs. The tornado outbreak was one limb, the flooding is another, the freeze is a third, and the reload we're about to watch on April 23rd is the next limb extending out of the same body. You do not get this kind of coordinated sequence from random atmospheric noise, you get it from a system that has a dominant driver pushing it forward. Think of it this way, the normal atmospheric pattern is like a series of firecrackers going off in a field. Each one is loud, each one is brief, and between each one there is silence. What we are watching right now is not firecrackers. It is a conveyor belt. The belt keeps moving. The next package keeps arriving. The machinery does not pause between deliveries because the machinery is not designed to pause. It is designed to keep producing, and as long as the driver behind it stays in place, it will keep doing exactly that. And this is where the central thread tightens, because a conveyor belt implies a motor. A repeating pattern implies a forcing mechanism. A system that refuses to reset implies that something is holding the configuration in place, and that something is the same thing that made April 17th predictable in the first place. It is the same thing that made the April 23rd reload visible days in advance. It is the same thing that is quietly rewriting the rules for where severe weather is showing up this year, and where it is conspicuously absent. Each reload is building on the last. The ground is wetter than it should be. The soil is saturated in places it normally would not be in mid-April. The rivers are higher, the air masses clashing overhead are more pronounced. Every time the system pulses, it leaves the region slightly more loaded for the next pulse. And this hydrological and thermal continuity is one of the keys to understanding why the 2026 pattern is so structured, because the structure is being reinforced by the residue of each previous event. So when we get to April 23rd, we are not watching a fresh weather system arrive on a clean slate. We are watching the next wave hit ground that is still wet, air that is still charged, and a jet stream that is still locked into position. And what that wave is about to produce is something that, in any other year, would be the biggest weather story of the month. This year, it is just the next scheduled delivery on a conveyor belt that nobody seems to be able to shut off. And the shape of what it is about to produce is going to tell you everything you need to know about the driver behind all of this. Part 3. The Quad Hazard Event. The Signature. If you want to understand why meteorologists are starting to get quiet and careful when they talk about the 2026 season, you need to look at what is coming together for April 23rd. And I want you to pay close attention here, because this is not just another severe weather day. This is the kind of day that, when you list out what it is going to do simultaneously, sounds like somebody's making it up. Across the plains and Midwest, a tornado outbreak is lining up. Same geography as April 17th, same set of ingredients, same risk categories. At the same time, across Montana and Wyoming, blizzard conditions are expected, with heavy snow and winds that could reduce visibility to zero and strand travelers for hours. At the same time, across Texas, Oklahoma and Kansas, critical fire weather is in the forecast, with red flag warnings being drawn up for conditions so dry and windy that a single spark could spread for miles before anyone could get ahead of it. And at the same time, across the upper Midwest, flooding is intensifying, with rivers already swollen from the last system now receiving another round of heavy rain on top of the first. Tornadoes, blizzards, fires, floods, all on the same day, all from the same system. Now stop for a second and think about what you just read. In a normal year, any one of those hazards would be a major story on its own. Any one of them would dominate the weather coverage for a full news cycle. You do not normally get a tornado outbreak and a blizzard on the same day, because those two hazards require fundamentally different atmospheric setups. Tornadoes need warm, moist, unstable air. Blizzards need cold, dense, dry air. They live in different temperature zones, different humidity zones, different pressure regimes, and yet here they are, on the same calendar date, inside the same synoptic system, separated by only a few hundred miles of geography. And that is where the compound event concept comes in, because what you are watching is not 4 separate weather stories. It is one atmospheric engine producing 4 different outputs at the same time, and the reason it can do that comes down to the structure of the system itself. At the centre of it is a deep upper-level trough ejecting out of the Rockies, with a strong surface low-pressure system forecast to drop to around 987 millibars. That is a seriously deep low for late April. That is the kind of pressure signature you expect in a winter nor'easter, not a spring plains system. And when you get a low that deep, with moisture streaming up from the Gulf on one side and cold Canadian air wrapping around on the other, you get a machine that can produce every kind of severe weather at once. The warm sector on the eastern and southeastern side of the low pulls Gulf moisture northward, loads it with instability, and meets it with the wind shear coming off the jet stream overhead. That is your tornado factory. The cold sector on the northern and western side wraps cold dry air around the back of the low, and when that cold air meets any residual moisture, you get heavy snow and blizzard conditions. The dry line, that invisible boundary on the southern edge of the system where moist Gulf air meets dry desert air from the southwest, gets pulled eastward into Texas and Oklahoma, and the air to the west of it becomes a tinderbox. 90+ degree temperatures, humidity values crashing to 5 or 15%, wind gusts tearing across the prairie, and any fire that starts in that zone is going to run for miles. One system, 4 hazards, all driven by the same atmospheric engine, and this is where the 2026 pattern starts to feel less like weather and more like a signature, because multi-hazard compound events on this scale are not the norm. They happen, but they are rare enough that when they do, researchers write papers about them. The fact that we are getting one of these as the next scheduled reload, in a repeating pattern, tells you that whatever is driving the pattern is pushing very hard on the atmosphere, hard enough to produce compound events as part of the routine. And when we talk about the fire risk specifically, it is worth pausing on the numbers because they are startling. We are looking at conditions in the 90th percentile for dryness across parts of the southern plains, relative humidity values dropping into single digits in the driest pockets. That is not a little dry. That is the kind of dry where you can feel static electricity on your skin when you walk across a room. That is the kind of dry where vegetation becomes fuel in a way that it almost never is in April. Most years, the southern plains are still green enough and humid enough in late April that fire weather is not the top concern. This year, on the same day that we are watching tornadoes in Kansas, we are watching red flag warnings in Texas. This is what I mean when I say coordination rather than complexity. A complex weather day is one where a lot is happening in a disorganized way. A coordinated weather day is one where a lot is happening in an organized way, driven by a single underlying cause, distributed across different regions in a sensible pattern that reflects the structure of the driver. April 23rd is coordinated. The dry line is where it should be. The warm sector is where it should be. The cold wraparound is where it should be. Everything is in position. Everything is doing its job. And that is precisely what should worry you. Because coordination on this scale, from a system that is the next reload in a repeating pattern, is exactly what you would expect if there were a dominant atmospheric driver locking the jet stream into position and pushing troughs through the west on a schedule. And the pattern producing this quad hazard event is the same pattern that produced April 17th. It is the same pattern that produced the sequence of outbreaks earlier in April. And it is going to keep producing events like this as long as the driver behind it stays in place. And that driver, as we're about to unpack, is not something that is going to go away in the next few weeks. If anything, it is about to get stronger. But before we get to that, there is something about the timing of these events, the spacing, the cadence, that nobody seems to be talking about, and it is maybe the clearest fingerprint of all. Part 4. The cadence nobody's talking about. I want you to look at a calendar with me for a moment, because if you lay out the 2026 tornado season on a timeline, you start to see something that is not supposed to be there. Between April 1st and April 5th, there was a sequence of outbreaks across the central United States. Then, between April 9th and April 16th, another sequence, then the April 17th outbreak itself, which was really the culmination of a setup that had been building for days. And now, between April 22nd and April 26th, the next system is arriving, with April 23rd as the peak risk day. Look at the spacing, roughly 6 to 8 days between major events. Not 5, not 12, 6 to 8, every time. And that kind of regularity is not what the atmosphere does when it is behaving randomly. Random does not produce even spacing. Random produces clumps and gaps. You get 3 outbreaks in 10 days, then nothing for 3 weeks, then 2 outbreaks in a single week. That is what a chaotic tornado season looks like on a calendar. Even spacing, by contrast, is the signature of a cycle. And a cycle implies a mechanism. This is the cadence nobody is talking about, and it is one of the clearest indicators that the 2026 season is being driven by something larger than local conditions. Because when you see periodicity in atmospheric behaviour on this scale, it means the atmosphere is oscillating in response to a dominant forcing. The forcing is setting the beat, and the storms are landing on that beat. 6 to 8 days between Pacific trough ejections is not a coincidence. It is a fingerprint. Here is what is physically happening. The jet stream, that high-altitude river of fast-moving air that steers weather systems across the continent, is locked into a configuration that keeps sending waves of energy eastward from the Pacific. Each wave is what meteorologists call a trough, a southward dip in the jet stream that pulls cold air down and allows warm, moist air to surge northward ahead of it. When a trough ejects out of the Pacific and moves over the Rocky Mountains, the downstream result, over the plains and Midwest, is the kind of setup that produces severe weather. And because the jet stream configuration is persistent, the troughs keep coming, one after another, on a schedule. 6 to 8 days is roughly how long it takes for one trough to move through and the next one to arrive. That number is not arbitrary. It reflects the wavelength of the Rossby waves that govern jet stream behaviour in this particular configuration. And when you see that wavelength repeating itself across a whole month of weather events, you know you are looking at a stable atmospheric regime, not a series of unrelated storms. Compare this to what a random distribution of severe weather events would look like. If the atmosphere were truly chaotic, you would expect the time between outbreaks to follow something like a Poisson distribution. Sometimes 2 days, sometimes 12, sometimes a whole month of quiet followed by 3 outbreaks in a single week. That is not what 2026 is doing. 2026 is pulsing, and pulses come from drivers. This brings us to the concept of teleconnections, which is a word you should get comfortable with if you want to understand why this season is behaving the way it is. A teleconnection is a large-scale climate pattern that influences weather over wide regions by altering atmospheric circulation. The most famous teleconnection is El Niño Southern Oscillation, or ENSO, which I will keep referring to throughout this video because it is the central character in this story. ENSO influences the jet stream. The jet stream influences where troughs form and how often they eject, and that, in turn, influences where and when severe weather happens. So when I tell you that the 2026 tornado season is pulsing on a 6 to 8 day cadence, what I am really telling you is that a teleconnection is driving the timing. The jet stream is locked into a pattern. The pattern is producing troughs on a schedule, and the troughs are producing outbreaks on the downstream side. Pulse, reload, pulse, reload. Each event looks like a separate storm, but they are all expressions of the same underlying configuration. Let me give you a visual that might help this land. Imagine a factory assembly line that produces the same product over and over again. Each product comes off the line at a regular interval, every 6 minutes, say. Now imagine you're standing at the end of the line and you see product after product roll out, each one essentially identical to the last. You might be tempted to think of each product as a separate thing, but really they are all the same thing, manufactured by the same machinery, emerging at the pace the machinery dictates. That is what we are watching in the atmosphere right now. One pattern expressing itself multiple times on a schedule that reflects the speed of the machinery producing it. And this reframes everything. Because if 2026 is one pattern expressing itself multiple times, then the question is no longer, when will the next outbreak happen? The question becomes, when will the pattern end? And the answer to that question depends on what is driving the pattern, how persistent that driver is, and whether it is going to weaken or strengthen in the weeks ahead. Those are not forecasting questions. Those are regime questions. And the atmosphere is telling us very clearly that we are in a regime, not a series of accidents. But even that is not the whole picture, because the most telling piece of evidence for this pattern is not in what is happening. It is in what is conspicuously not happening. And to find that missing piece, you have to look several hundred miles southeast of where all the action is. You have to look at a region that should be the epicenter of severe weather right now, and is instead eerily, unsettlingly quiet. Part 5. The Missing Signal. Here is where the story takes its strangest turn, and it is the turn that convinced me this video needed to be made. Because the biggest clue about what is driving the 2026 tornado season is not in what is happening in Wisconsin or Kansas or Oklahoma. It is in what is not happening somewhere else entirely. And until you see the absence, you cannot see the shape of the pattern as a whole. I want you to think about where tornadoes are supposed to be happening right now. If you asked a meteorologist in, say, 2019, where would you expect peak severe weather activity in mid to late April? The answer would not have been the Northern Plains. The answer would have been Dixie Alley. That is the region that covers Mississippi, Alabama, Tennessee, and the surrounding states. It is a region that, over the past 2 decades, has become one of the most dangerous severe weather zones on the planet, responsible for some of the deadliest tornado outbreaks in American history. And historically, its peak season runs from late winter into early spring, with March and April being the months of heaviest activity. Dixie Alley in April is supposed to be loud. It is supposed to be active. It is supposed to be producing long-track tornadoes at night, rain-wrapped violent storms that run across multiple states, the kind of events that fill the weather news cycle and keep forecasters from sleeping. That is the baseline. That is what the last 5 Aprils looked like in that region, to varying degrees. 2026 is silent. Dixie Alley is having its quietest severe weather spring in 5 years, and this is not a subjective impression. This is something that multiple severe weather analysts have now confirmed by looking at the numbers. The number of Storm Prediction Center enhanced risk days over the southeast this spring is dramatically lower than the recent baseline. The number of tornado reports is down. The number of significant severe weather events is down. Across the board, the region that should be the loudest part of the country right now is barely making noise. And before you start thinking this is just random year-to-year variability, I want you to sit with the contrast for a minute. The plains and Midwest are overloaded. They are getting hit with outbreak after outbreak on a 6 to 8 day cycle, with compound multi-hazard events forming the reloads. The Southeast at the same time is experiencing its quietest spring in half a decade. One region is drowning in severe weather. The other region is having what could almost be described as a calm spring. And these two things are happening simultaneously, across a landmass that shares the same overall weather system. That is not normal variability. Normal variability gives you years where the Southeast is quieter than average, sure, but it does not typically give you years where the plains are overloaded and the Southeast is underloaded in such a clean, mirrored way. When you see that kind of redistribution, that kind of clear geographic displacement of severe weather from one region to another, you're not looking at chance. You're looking at a climate signal that is rearranging where the ingredients are assembling, and this is where the central thread tightens its grip. Because the 2026 pattern is not defined only by what it is producing, it is also defined by what it is suppressing. The energy that would normally be driving late-night tornado outbreaks across Alabama and Mississippi is not missing. It is somewhere else. It has been relocated, and the question of where it went and why is the question that unlocks the entire story. So here is what you need to hold in your head as we move into the next section. The atmosphere on April 17th was not just active in the Midwest, it was simultaneously inactive in the Southeast. These are two halves of the same phenomenon. One region is getting the full force of the pattern, and the other region is watching the show from the sidelines. And when you understand why that redistribution is happening, you understand why 2026 is not a random tornado season. It is a textbook illustration of a specific atmospheric regime playing out in real time, almost exactly the way it was predicted to play out in a peer-reviewed study published in 2015. Something is redistributing the atmospheric ingredients this spring. Something is telling moisture, shear, instability, and lift where to assemble and where not to. And the mechanism behind that redistribution is about to become the main character in this story, because once you see it, you cannot unsee it, and the 2026 season stops looking like weather and starts looking like choreography. Part 6. Dixie Alley should be active right now. Let me give you a quick picture of what Dixie Alley looks like when it is doing what it normally does, because without that baseline, the silence does not land the way it should. Dixie Alley storms are in many ways the most dangerous severe weather in the country. They tend to form at night, which means people are asleep when the sirens go off, if they hear them at all. They tend to be rain-wrapped. which means the tornado is hidden inside a curtain of heavy precipitation and is almost impossible to see until it is directly on top of you. They tend to move fast because the low-level jet is often roaring at 40 to 60 knots across the region during peak events. And they tend to occur in areas with higher population density and more manufactured housing than the open plains, which is a significant part of why Dixie Alley tornadoes have historically had higher fatality rates than their Great Plains counterparts. The seasonal timing for this region runs heavy from late February into early May, with March and April being the peak months. This is when the Gulf of Mexico is warm enough to pump serious moisture northward, the jet stream is active enough to provide the wind shear, and the clash between lingering cold air masses to the north and warm, moist air masses to the south is strong enough to generate the instability. Under normal conditions, you would expect to see enhanced or moderate risk days from the Storm Prediction Center firing off over this region on a regular basis during this window. You would expect multi-state outbreaks. You would expect news coverage. You would expect the standard rhythm of spring severe weather in the southeast to be running at full volume. If you look at the data from 2021 through 2025, that is exactly what you see. Year after year, the southeast has been contributing a large share of the nation's tornado count during the early and middle parts of spring. Some years more intensely than others, but always with a recognizable signal. 2026 deviates from this baseline in a way that is hard to ignore. The number of enhanced risk days over the southeast this spring is noticeably lower. The outlook maps that should be coloured in with oranges and reds over Alabama and Mississippi have instead been coloured in with yellows and greens, or have shifted northwest entirely. The storm reports that should be flooding in from the region are a trickle compared to the historical average. Analysts who watch this region closely have been commenting on it for weeks. This is not one person's read on the data. This is an observational consensus that something unusual is happening. And I know this is a secondary topic in the broader story, but I want to be clear about why it matters to the main thread. It matters because the southeast is typically a major contributor to the national tornado count in early and mid-spring. Its suppression this year is not cosmetic. It is the other half of the pattern we have been tracing. The plains and Midwest are overloaded because the southeast is underloaded. The energy that would normally be driving outbreaks across Dixie Alley is being routed north and west, and that redirection is exactly what a specific climate driver would produce if it were in control of the jet stream this spring. Which is to say, Dixie Alley is not silent by accident. It is silent by design. Its silence is the direct, predictable consequence of the same driver that is producing the cadence we identified in the last section. The same driver that is making the quad hazard events possible. The same driver that's keeping the atmosphere from resetting between outbreaks. The absence in the southeast and the presence in the Midwest are two symptoms of a single underlying condition, and that condition is exactly what the peer-reviewed climate science we're about to dive into says should happen when the Pacific Ocean shifts toward a warm phase. So when you feel the strangeness of a quiet April in Dixie Alley, do not file it away as an odd year. File it as confirmation. The rulebook says Dixie Alley should be quiet under these conditions. The atmosphere is following the rulebook. And the fact that it is following the rulebook this cleanly is exactly why the whole 2026 season feels so structured, so predictable, and so unsettling once you see what is really going on. Part 7. The energy went somewhere else. So where did it go? If Dixie Alley is quiet, and the plains and Midwest are loud, the energy has to have gone somewhere, because energy in an atmospheric system does not simply disappear. It gets redistributed, it finds a new home, it expresses itself in a different place. And mapping that redistribution is one of the most revealing exercises you can do this spring, because it shows you exactly how the 2026 pattern is reorganizing the country's severe weather geography. Look at the map. The activity has shifted northward and westward. Instead of a belt of severe weather running from Texas through Louisiana, Mississippi, Alabama, and into Georgia and the Carolinas, which is the classic late winter to early spring pattern, we're seeing a belt that runs from Texas north through Oklahoma, Kansas, Nebraska, Iowa, and up into Wisconsin and Minnesota. The heart of the action is not in the deep south, it is in the central and northern plains and the upper Midwest, and the Storm Prediction Center outlooks confirm this visually day after day, with the enhanced and moderate risk polygons being drawn farther north than they typically would be this time of year. The ingredients themselves, the moisture, the wind shear, The instability, the forcing, have been redistributed. The Gulf moisture is still being pulled north, but it is being pulled farther north before it meets the strongest shear and lift. The jet stream is positioned in a way that routes the trough ejections over the northern plains rather than over the southeast. The surface low-pressure systems are tracking through the upper Midwest rather than through the Tennessee Valley. All the same pieces, but assembled in a different place. This is what redistribution looks like in atmospheric terms. The total amount of severe weather this spring may not be dramatically different from an average year. The total tornado count by the time we reach the end of May may even be in the normal range. But the geography of where that severe weather is happening is radically different, and that is the piece that matters, because it is the geography that tells you who is at risk, when they are at risk, and what kind of preparation they should be doing. And here is the part that ties this back to everything we have been building. Redistribution is exactly what a specific climate driver predicts. Not random variation, not noise, redistribution. When the Pacific Ocean is in a certain state, the jet stream adopts a certain configuration, and that configuration routes severe weather into specific regions and away from others. This is not speculation. This is mechanism. And the mechanism is well documented in the climate science literature, as we're about to see. From the viewer's perspective, especially if you live in the plains or the Midwest, this season might feel like there are just more storms than usual. It might feel like things are getting worse, like the atmosphere is more active, like something is ramping up, and in a local sense that perception is accurate. Those regions are getting more severe weather than they would in an average year, but nationally the story is a little different. The total amount of severe weather is not necessarily higher, it is just concentrated in fewer regions, which makes those regions feel overloaded, while other regions, like Dixie Alley, feel eerily quiet. Same regions are being hit repeatedly. The April 1st through 5th sequence hit the Central Plains and Midwest. The April 9th through 16th sequence hit roughly the same area. The April 17th outbreak was centered over Wisconsin and the upper Midwest. And the April 23rd event is forecast to hit the plains and Midwest again. Same ingredients, same geography, same targeting. That is not how a typical season distributes itself. A typical season moves around. 2026 is parking its systems in the same zip code over and over again, and that consistency is what tells you the jet stream is locked. Now some of you are probably thinking, okay, but how do we know this is actually being predicted by science? How do we know this is not just a coincidence that happens to line up with a general theory? And that is a fair question. It is the question I want you to be asking at this point, because it is the question that separates good analysis from hand-waving. So let us get into the statistical weirdness of what is happening, because when you look at the specific anomalies that have stacked up this spring, the argument that this is random becomes very, very difficult to maintain. Part 8. Statistical weirdness. Start with the EF3 tornadoes, because they are the easiest way to get a handle on what is happening. EF3 is the category that includes winds from 136 to 165 miles per hour. It is the threshold for what we would call strong or intense tornadoes. And the thing you have to understand about EF3 tornadoes is that they are rare. Out of all the tornadoes that touch down in the United States in a given year, only about 3% reach EF3 or higher intensity. The vast majority of tornadoes are EF0 or EF1, which do relatively minor damage. EF2 starts getting serious. EF3 starts flattening things. EF4 and EF5 are civilization reshaping events. On April 17th, 2 EF3s touched down in Wisconsin, 2 in the same state, on the same day, and that is before you start thinking about climatology. Because here is where the geographic weirdness kicks in. Wisconsin is not a typical hotspot for strong tornado clustering. It gets tornadoes, of course. The state is solidly in the zone of the country that sees severe weather on a regular basis, but when you look at the climatology of strong and violent tornadoes, the heaviest concentration has historically been in the Great Plains, especially Oklahoma, Kansas, Texas, and Nebraska. The secondary concentration is in Dixie Alley, especially Alabama, Mississippi, and Tennessee. Wisconsin, while not immune, is not at the top of the list for strong tornado activity, particularly in any given year. For Wisconsin to produce 2 EF3 tornadoes in a single outbreak is an event that, in any other year, would be a statewide weather story on its own. In 2026, it is one data point in a much larger pattern of northward displacement, and that is the key word: displacement. The tornado density is shifting. The regions where strong tornadoes are clustering are moving, at least for this spring, away from their historical centres and into places that would not normally see this kind of activity. Compare this with historical averages for mid-April and the anomaly sharpens. In a typical mid-April, Wisconsin would be on the northern edge of the severe weather zone, occasionally seeing significant tornadoes but rarely seeing violent ones cluster in a single state on a single day. In 2026, Wisconsin is at or near the centre of the severe weather zone, and the violent tornadoes are clustering there. Same state, very different climatological role, and this is where the concept of outliers clustering together becomes important. Because you can get one unusual tornado in an unusual place and shrug it off. That happens. Weather is messy. Strange things occur from time to time. But when you start stacking unusual events on top of each other, and each one individually is already an anomaly, the combined probability of all of them happening by chance drops very fast. Think about it. In April of 2026, we have seen a pattern that includes an unusually high number of outbreaks, occurring on an unusually regular cadence, with an unusually consistent geographic footprint that is shifted unusually far north and west of the historical norm, featuring unusually strong tornadoes clustering in unusually unlikely states, during a period when Dixie Alley is unusually quiet. That is not one anomaly. That is 6 or 7 anomalies, all pointing in the same direction, all consistent with a single underlying driver. When anomalies stack like that, they stop being statistical noise, they start being signal. And the key thing is that each of these anomalies, taken individually, might be plausible as chance. 2 EF3s in Wisconsin, unusual but possible. A quiet April in Dixie Alley, happens sometimes. A 6 to 8 day cadence of outbreaks, could be coincidence. But when you multiply the probabilities of all of them happening together, you get a number that is effectively 0 for a randomly behaving atmosphere. The only way to get this many anomalies aligning this cleanly is if there is a system-level driver producing all of them at once. Which is why, when I tell you that 2026 is not random, I am not speculating. I am telling you what the statistics require. The statistical weirdness of this spring is so pronounced that the null hypothesis of random atmospheric behaviour essentially fails. Something is coordinating these anomalies. Something is the common thread. And the explanation, as we will see, has been sitting in a peer-reviewed journal for over a decade, waiting for a year like this to demonstrate its predictive power. But before we get to that, there is one more layer of the pattern that I want to address, because it is the layer that explains why so many people are not seeing what is happening even though it is happening in front of them. It is the cognitive layer. The way humans perceive weather events, the way we categorize seasons, the way we decide what counts as normal. Because the 2026 season, on the surface, looks normal, and that surface normality is hiding one of the most structured severe weather patterns we have seen in years. Part 9. The illusion of normal. There is a very casual, very common response to what I have been describing, and it goes something like this. There are always tornadoes in April. This is just what spring looks like in the middle of the country. Why are you making a big deal out of it? And I want to address that response head on, because the instinct behind it is exactly what is allowing this pattern to go largely unnoticed by the general public, even as forecasters and climate scientists are watching it with increasing unease. The human brain is wired to track events, not patterns. When you see a news clip of a tornado, your brain categorizes it as tornado happened. When you see another clip a week later, your brain categorizes that as another tornado happened. The events get filed as separate items in memory, and unless you deliberately overlay them on a map and a calendar, you do not naturally perceive the geometry of the season as a whole. You perceive a sequence of similar events, which matches your mental model of this is what spring looks like, and the pattern underneath stays invisible. This is a known cognitive bias, and it is not a flaw so much as a feature of how we process information. We are event trackers, not pattern recognizers, at least not without effort. And so a highly structured season like 2026 can hide in plain sight, because the events themselves, taken individually, look like events you have seen before. Tornadoes in April, floods in the Midwest, red flag warnings in the plains. Each of these, on its own, is familiar. The fact that they are all showing up on the same day, in a repeating cadence, as part of a coordinated pattern, is the piece that requires deliberate analysis to see. This is where the expert versus public perception gap comes in. Meteorologists and climate scientists have been watching the 2026 pattern with growing concern because they are trained to look at the overlays, they look at the outlook maps over time, they compare cadences, they track the geographic footprint, they compute the statistics, and when they do that, they see what I have been describing in this video. The public, meanwhile, sees tornadoes on the news and thinks, yeah, it is April in the Midwest, this is what happens. And both perceptions are understandable, but only one of them is actually accurate. The season only looks normal on the surface. Underneath, it is one of the most structured, most coordinated, most theoretically predictable, severe weather patterns we have seen in years. And the gap between what it looks like at a glance and what it actually is under analysis is a big part of why the implications of this pattern are not being discussed as widely as they probably should be. Which brings me back to the central thread. The 2026 season is not random, it is structured. The reason it looks normal is not because it is normal, it is because the structure is hidden inside events that match our existing mental templates of what spring weather is supposed to look like. Peel back that surface familiarity, and what you find underneath is an atmosphere following a script. A script that was, as we're about to see, written in a research paper in 2015 and is now being played out in real time over the American heartland. Part 10. Two signals colliding. Before we get to that paper, there is one more piece of context that you need, because it explains why 2026 is behaving the way it is in a way that runs counter to what long-term climate trends would predict. And it is a genuinely fascinating wrinkle in the story, because it shows you that the atmosphere is being pulled in two different directions at once, with one force winning for now and the other force waiting its turn. The long-term trend, over the past several decades, has been for tornado activity to shift eastward in the United States. Research from the National Oceanic and Atmospheric Administration's National Severe Storms Laboratory and a number of peer-reviewed studies has documented this eastward migration. The classic tornado alley, centered over Oklahoma, Kansas and Texas, is seeing relatively fewer tornadoes than it used to, while the southeast, particularly the mid-south and parts of the Ohio Valley, is seeing more. The reasons for this are complex and still actively debated, but they involve long-term changes in moisture patterns, changes in instability distributions, and possibly shifts in the behavior of the jet stream over decadal timescales. Now, if the long-term trend is eastward, you would expect Dixie Alley to be increasingly active relative to the plains over time. That is the direction the climate signal is pointing. Over the course of decades, the southeast is supposed to be becoming more of a tornado hotspot, not less. So what are we looking at in 2026, where the southeast is quiet and the plains are overloaded? That is the opposite of what the long-term trend predicts. What we are looking at is competing climate signals operating on different timescales. The long-term trend, the decadal climate signal, says more activity in the southeast, less in the plains. The short-term driver, the seasonal climate signal, says more activity in the plains, less in the southeast. And for this particular spring, the seasonal driver is winning. It is overriding the long-term trend. This is an important distinction, because it tells you that climate signals do not all move in the same direction at the same time. You can have a long-term trend pointing one way, and a short-term driver pointing the other way, and the short-term driver can dominate for a period of months or a year. That is what is happening right now, and the specific short-term driver that is dominating in 2026 is ENSO, which, as I mentioned earlier, operates on a seasonal to interannual timescale and has a powerful influence on the jet stream. And this is where the central thread picks back up, because the reason the plains are overloaded and the southeast is quiet this spring is not in contradiction with the long-term trend. It is in superposition with it. The long-term trend is still there, still pushing tornado activity eastward on decadal timescales. It just happens to be temporarily overwhelmed by an ENSO-driven regime that is rerouting activity westward and northward for this particular season. When the ENSO signal weakens, as it will eventually, the long-term trend will reassert itself, and the southeast will likely resume its role as a major tornado zone. But for right now, for this spring, ENSO is the boss, and the pattern it is producing is the pattern we have been tracing for the past 40 minutes of your attention. Structured cadence, geographic redistribution, statistical weirdness, quad-hazard compound events, a southeast that is unnervingly quiet. All of it is the signature of a specific ENSO configuration reaching into the atmosphere and telling it where to put severe weather this spring, and that configuration and the science behind how it works is where we go next. Part 11, the 2015. Prediction that's now playing out. In 2015, a team of researchers at Columbia University's International Research Institute for Climate and Society published a study that should now, in light of what we're seeing this spring, be on every meteorologist's desk and every weather enthusiast's reading list. The authors, John Allen, Michael Tippett, and Adam Sobel, published their work in a peer-reviewed journal, and the central finding was both elegant and deeply consequential. They demonstrated quantitatively that the El Niño Southern Oscillation modulates the geography of severe weather in the United States in specific predictable ways, not vaguely, not approximately, specifically. Let me pause here because I want you to feel the weight of what that means. This was not a speculative piece. This was not a think piece in a popular magazine. This was a rigorous, peer-reviewed, quantitative study that looked at decades of historical data on severe weather and ENSO phases and established a statistical relationship between the two that was robust enough to produce predictive skill. In other words, they built a rulebook. They said, in effect, when the Pacific looks like this, severe weather will tend to happen over here, and when the Pacific looks like that, severe weather will tend to happen over there. And they backed that rulebook up with the math. The mechanism they identified is not mysterious once you lay it out. It goes like this. Sea surface temperatures in the tropical Pacific Ocean influence atmospheric convection patterns in the tropics. Those convection patterns, in turn, influence the position and strength of the jet stream over the Pacific. The jet stream configuration over the Pacific propagates downstream and affects the position and strength of the jet stream over North America. And the jet stream over North America determines where troughs form, where surface low-pressure systems track, where Gulf moisture is drawn northward, and where the clash of air masses that produces severe weather tends to set up. Pacific temperature to jet stream position to storm track to severe weather geography, a direct chain, a causal mechanism, a rulebook. Under an El Niño signal, the pattern tends to favour the plains and Midwest for severe weather activity in early to mid-spring, while suppressing activity across the southeast. Under a La Niña signal, the pattern tends to do something closer to the reverse, with enhanced activity across Dixie Alley and reduced activity across parts of the plains. The specifics are more nuanced than that, and the exact regional signals depend on the strength of the ENSO phase and the time of year, but the basic rulebook is well established. Now compare the rulebook to what we are actually seeing in 2026. Plains and Midwest, overloaded with outbreaks. Southeast, conspicuously quiet. Geographic shift northward and westward relative to historical norms. Coordinated cadence consistent with a persistent jet stream configuration. That is not a rough match. That is a textbook match. The pattern the Columbia team described in 2015 is being demonstrated with unusual clarity in the spring of 2026. It is almost as if somebody took their paper, drew the expected regional signals on a map, and then watched the atmosphere colour inside the lines. And the predictive power of this is what should stop you in your tracks. Because the paper was published years before the current season. Years before anyone knew what the Pacific Ocean would be doing in April of 2026. And yet the rulebook it established has turned out to describe this spring with remarkable accuracy. That is not coincidence. That is science working the way science is supposed to work. You build a model, you test it against future data, and if the model keeps predicting correctly, you gain confidence that it is capturing something real about the physical world. We have seen this before, on paper, long before it showed up on radar, and that is exactly why the 2026 season is not a surprise, it is a confirmation. The April 17th outbreak confirmed the rulebook. The April 23rd reload is going to confirm it again. The Dixie Alley silence is confirming it in real time. Every data point this spring is landing in the place the rulebook said it should land, and the cumulative weight of those confirmations is what makes this season so distinctive. But there is a twist, and this is the part that escalates everything we have been discussing. We're not even fully in El Niño yet. The Pacific is still drifting toward the warm phase. The atmospheric response we're seeing right now is what happens when the ocean is leaning in that direction, not when it has fully committed. And that raises a question that nobody in my position can avoid asking. If the pre-El Niño signal is already producing a season this structured, this destructive, this coordinated, what is the full El Niño signal going to look like when it arrives? Before we answer that, we need to understand the rulebook in more detail because the specific phase structure of ENSO matters, and the way it translates into severe weather geography is worth understanding on its own terms. Part 12. The Rulebook. ENSO is not a single state. It is an oscillation, meaning it cycles between three main phases over time. There is El Niño, which is characterized by warmer than average sea surface temperatures in the central and eastern tropical Pacific. There is La Niña, which is characterized by cooler than average sea surface temperatures in the same region. And there is ENSO neutral, which is the in-between state where conditions are neither clearly warm nor clearly cool. The transitions between these phases happen over timescales of months to years, and each phase tends to produce distinctive weather patterns across large parts of the globe, including the United States. Under La Niña conditions, the pattern across the continental United States in late winter and early spring tends to favour severe weather activity across the southeast. The jet stream configuration under La Niña tends to keep the storm track farther south, allowing Gulf moisture and the clash of air masses to set up over the Mid-South and the Tennessee Valley more readily. This is part of why recent springs, when La Niña has been influential, have seen major outbreaks in Dixie Alley. Not the only reason, but an important one. Under El Niño conditions, the pattern shifts. The jet stream tends to take a more southerly route across the Pacific and into the southern tier of the United States, which actually routes moisture and storm systems in ways that favour activity farther north, over the central plains and Midwest during the transition from late winter to spring. The southeast tends to see reduced severe weather activity under many El Niño configurations in this season because the storm track is repositioned and the ingredients do not assemble there as readily. This is a simplification of a complex picture, and the exact effects depend on the strength of the El Niño, the time of year, and other overlapping factors. But the basic signal is there, and it is the signal that the Columbia team quantified in 2015. And this rulebook is not based on a single event or a single season. It is based on decades of historical data, which means it represents a statistical relationship that has been observed repeatedly across many different ENSO cycles. When La Niña shows up, the pattern tends to look a certain way. When El Niño shows up, the pattern tends to look a different way. This kind of repeatability across multiple decades is exactly what you want to see when you're trying to establish a causal relationship, as opposed to a random correlation. It is the difference between one anecdote and a population of observations that share a common signature. The physical drivers behind the rulebook are well established. Sea surface temperatures in the tropical Pacific influence atmospheric convection through heating of the overlying air. Changes in tropical convection propagate outward through atmospheric waves, which shift the position and strength of the jet stream at higher latitudes. Shifts in the jet stream influence where surface low-pressure systems form and track, which influences where moisture is pulled in and where the ingredients for severe weather assemble. This is not a mysterious black box. It is a well-understood chain of physical processes, each step of which can be measured and modelled, and each step of which contributes to the overall pattern. This is not random correlation. It is a causal mechanism that has been studied, quantified, and validated across multiple independent investigations. The 2015 Columbia paper is one particularly influential piece of that larger body of research, and its specific contribution was to establish predictive skill for severe weather geography based on ENSO state. But it is not a lone voice. It is part of a broader consensus in climate science that ENSO is one of the most important modulators of year-to-year severe weather variability in the United States. What the rulebook tells us, in the context of 2026, is that the atmosphere is following rules, not throwing dice. When certain conditions are in place, certain patterns emerge. The complexity of the real atmosphere introduces noise around those patterns, but the signal underneath is real, and this spring, the signal is unusually clean, which is why the pattern is so recognizable. 2026 fits the rulebook with a precision that, frankly, is unusual. Most seasons you see echoes of the expected pattern, with a lot of noise layered on top. This season, the pattern is emerging with unusual clarity. The signal-to-noise ratio is high, and that high signal-to-noise ratio is itself a data point worth paying attention to, because it tells you that whatever is driving this spring is driving it hard. So where exactly are we in the ENSO cycle right now? That is the question we have to answer next, because it determines how we should interpret what we have been watching and what we should expect in the weeks and months ahead. Part 13, where we actually are right now. The technical answer is that we are currently in an ENSO-neutral state that is trending warm. The Oceanic Niño Index, which is the standard measure of ENSO state, has been climbing, moving from a reading around negative 0.55 to a reading around negative 0.16 over recent months. For those who are not familiar with the index, readings above positive 0.5 are considered El Niño conditions, readings below negative 0.5 are considered La Niña conditions, and anything in between is considered neutral, so negative 0.16 is on the neutral side of the scale. But it is trending in the warm direction, fast, and that is just the surface signal. Beneath the surface, the story is more dramatic. There is significant subsurface warming in the equatorial Pacific, including a Kelvin wave with anomalies around positive 4 degrees Celsius propagating eastward. A Kelvin wave in this context is a large, slow-moving wave of warm water that travels along the equator and eventually surfaces, contributing to the transition from neutral or La Niña conditions to El Niño conditions. When you see a strong Kelvin wave like this, it is a harbinger. It is telling you that the ocean is loading up to push the surface temperatures higher over the coming months. Now here is the thing about the atmospheric response to ENSO that is easy to miss if you are not tracking it carefully. The atmosphere does not wait for the ENSO index to cross some official threshold before it starts responding. The atmosphere reads the ocean's state in real time, and it begins adjusting its circulation patterns based on what the ocean is actually doing, not based on what some index classification says about the state. So even though we are technically still in ENSO-neutral territory, the atmosphere is already starting to behave as if an El Niño is underway, because it is responding to the oceanic signal that is building, not to the index value. This is crucial context for understanding the 2026 season. What we are watching right now is not the atmospheric response to a fully developed El Niño. It is the atmospheric response to a pre-El Niño configuration, where the Pacific is leaning warm and the atmosphere is starting to adopt the circulation patterns that El Niño tends to produce. The pattern is in its early stages, the forcing is not yet at full strength, and yet the pattern is already producing the structured, coordinated, cadenced, severe weather season that we have been documenting. Pre-El Niño behaviour. That is the key phrase. The atmosphere is already responding to where the ocean is going, not just to where the ocean is, and the response we are seeing is what the rulebook predicts for this early phase of the transition. Plains and Midwest activity, southeast suppression, persistent jet stream configuration producing a regular cadence of trough ejections, coordinated compound events on the reload days. All of it is what you would expect given the current state of the Pacific and the atmospheric response that state produces. Which means, and this is the part that is hard to say without sounding alarmist, we have not seen the full expression of this pattern yet. What we have seen, as intense as it has been, is the appetizer. The main course is what happens when the El Niño signal fully develops and the atmospheric forcing intensifies, and that is a prospect that every forecaster and climate scientist watching this setup is aware of, even if they are measured in how they talk about it publicly. So if the early phase looks like this, with 54 tornado reports on April 17th, compound quad hazard events on April 23rd, a 6 to 8 day cadence of severe weather outbreaks, and Dixie Alley going silent, what does the full phase look like? What happens when the ocean fully commits and the atmosphere fully responds? Those are the questions we're going to dig into in the final act of this video, but first, I want to take a brief detour into something that has been nagging at me throughout the analysis, because it is one of the most unusual features of this season, and it deserves its own attention. Part 14, Why the Pattern Feels Too Clean. Weather systems are noisy. This is not a controversial statement. Ask any meteorologist and they will tell you that the atmosphere is a high-dimensional, chaotic fluid, full of small-scale variations that do not align with any large-scale signal. Most of the time, when you see a climate driver like ENSO influencing weather patterns, you see the influence as a tendency, not a rule. You see a bias in the statistics, not a perfect correspondence between theory and observation. The signal is there, but it's usually buried in a lot of noise, and you need to average over many events to see it clearly. Typical severe weather seasons, even ones with strong ENSO influence, reflect this noise. You get a general tendency toward the pattern the ENSO state predicts, but you also get a lot of individual events that do not fit. Outbreaks in unexpected places, quiet stretches in places that should be active, compound events that do not quite match the synoptic setup that would produce them cleanly. That is the normal state of affairs, and meteorologists are used to working within that messiness, extracting signal from noise where they can, and accepting that the atmosphere is ultimately unpredictable at the fine scale. The 2026 season does not look like that. It looks, if anything, too clean. The pattern that the Columbia team described in 2015 is emerging with a clarity that is unusual. The geographic redistribution is textbook. The cadence is regular. The Dixie Alley suppression is dramatic. The planes overloading is pronounced. The ingredients are showing up on schedule. The compound events are assembling as predicted by the synoptic structure. It is almost as if the noise has been turned down and the signal has been turned up. The signal-to-noise ratio this spring is unusually high. That is the best way to describe what is happening. The underlying pattern is emerging with more clarity than it typically does, because something is pushing on the atmosphere hard enough to overcome the usual noise and reveal the structure underneath. That something, almost certainly, is the strength of the Pacific forcing that is building even before El Niño has officially arrived. The Kelvin wave, the subsurface warming, the trending oceanic Niño index, all of these together are producing an atmospheric forcing that is unusually coherent, and that coherence is showing up in the severe weather pattern. A high signal-to-noise ratio in a climate-driven weather pattern is rare. It is the kind of thing that researchers notice. And it suggests that the forcing from the Pacific right now is unusually strong relative to the internal noise of the atmospheric system. In plainer terms, the Pacific is shouting, and the atmosphere is hearing it so clearly that the pattern it produces is almost textbook. This is where the central thread takes on a different emotional weight, because the clarity of the pattern is itself evidence that the pattern is structured, not random. A chaotic atmosphere would not produce this level of coherence. A randomly varying year-to-year signal would not align this cleanly with a published theory. The fact that the 2026 season looks like a perfect illustration of the 2015 Columbia paper is itself a data point, and the data point is telling us that the driver behind this season is powerful and persistent, and that clarity should inform how we think about what comes next. Because if the pre-El Niño signal is already producing a pattern this clean, the question of what a stronger ENSO signal would produce becomes urgent. Not because we should expect the pattern to get exactly cleaner, necessarily, but because the intensity of the forcing is likely to scale with the ENSO state, and a stronger forcing means a more pronounced pattern. More outbreaks, more coordinated events, more pronounced geographic redistribution. More of everything we have been watching potentially amplified. And this amplification would not be a surprise, because the machinery producing the pattern is well understood. It is the same machinery we have been tracing throughout this video, the same machinery that is about to get another demonstration in the next reload we will discuss, the weekly reload mechanism that is keeping this pattern alive. Part 15. The weekly reload mechanism. Let us put the physical pieces together, because understanding why the 2026 pattern is pulsing on a 6 to 8 day cadence is the key to understanding why it is likely to keep pulsing for as long as the underlying driver is in place. And the mechanism is actually beautiful, in the way that large-scale atmospheric processes can be beautiful once you see how they fit together. Troughs ejecting from the Pacific are the engine of this season. Here is what that means in practice. The jet stream, that high-altitude river of fast-moving air that girdles the mid-latitudes, is not a straight line. It meanders in a series of ridges and troughs. Ridges are northward bulges where the jet stream rises toward the pole. Troughs are southward dips where the jet stream plunges toward the equator. The ridge-trough structure is not static. It propagates eastward over time as Rossby waves, and the wavelength of those Rossby waves determines how far apart the ridges and troughs are in a given configuration. In the 2026 configuration, the jet stream is set up such that troughs are repeatedly ejecting from the Pacific, crossing the Rocky Mountains, and emerging into the central United States. Each trough brings a low-pressure system, a surge of warm, moist air from the Gulf ahead of it, and a clash with cold, dry air behind it. That clash is the ingredient cocktail that produces severe weather, and because the jet stream is locked into a persistent configuration, the troughs keep coming, one after another, on a schedule. The sequence inside each cycle goes something like this. First, a trough approaches from the west, visible on model forecasts several days out. As it approaches, the Gulf moisture starts to surge northward. Drawn up by the strengthening southerly flow ahead of the trough, the surface low-pressure system deepens as the trough moves over the Rockies, because the upper-level divergence aloft allows the surface pressure to drop. The warm sector, southeast of the low, becomes unstable and sheared, and the cold front on the western and northern edge of the low becomes the trigger. Storms fire along the dry line and the cold front, and if the parameters are right, tornadoes develop. The system then moves eastward over the next day or two, leaving a trail of severe weather and precipitation, before eventually dissipating or transitioning into a more mature extratropical cyclone farther east. And then the next trough arrives, and the cycle repeats. The reason the cycle repeats is because the jet stream configuration is persistent. The configuration is being held in place by the dominant climate driver, which is the Pacific forcing associated with the trending El Niño. As long as that forcing is in place, the jet stream will keep producing troughs at roughly the same cadence, and the atmosphere will keep responding with severe weather at the same spacing and in the same geography. 6 to 8 days is not an arbitrary number. It reflects the wavelength of the Rossby waves in this particular jet stream configuration. Different configurations would produce different wavelengths, and therefore different cadences. In this configuration, 6 to 8 days is what you get, and the consistency of that spacing across multiple events this spring is a direct signature of a stable atmospheric regime. This is an atmospheric feedback loop in the most literal sense. The ocean forces the jet stream produces the troughs produce the severe weather modifies the local environment in ways that, through hydrological and thermodynamic continuity, set the stage for the next trough's impact, and the cycle continues, each iteration building on the residue of the last, until the forcing changes. Same engine, different iterations. That is the right way to think about the 2026 tornado season. Each outbreak is not a separate event. It is a separate iteration of the same underlying machinery. April 1st through 5th was one iteration, April 9th through 16th was another, April 17th was another, April 23rd will be another. The iterations will keep coming as long as the machinery is running, and the machinery is being run by the Pacific Ocean. This reframes the entire season. We are not watching multiple events. We are watching one continuous system, expressed in multiple iterations, and that is why the pattern is so stable and so persistent. Stable systems do not come apart easily. They keep producing their output until the forcing that supports them changes, and the forcing here, the Pacific Ocean, is not only not weakening, it is strengthening. Which means the pattern is not only going to persist, it is likely to intensify. So what happens when the forcing increases? What happens when the Pacific fully commits to El Niño and the atmospheric response scales up accordingly? That is the question that hangs over the rest of this spring and into the summer, and it is the question we have to face in the final act of this video, because the answer is not comforting, and pretending otherwise would do a disservice to what the science is actually telling us. Part 16. If this is pre-El Niño. Let me ask you the question that every forecaster and climate scientist watching the Pacific right now is asking, at least in private. If the 2026 tornado season is this structured, this destructive, this coordinated, and this predictable, with the Pacific only drifting toward El Niño, what does the full arrival of El Niño do to the pattern? Because this is the central escalation question of the entire season, and the fact that we do not yet know the answer in detail does not mean we cannot reason about the likely direction of the answer. The most straightforward expectation is that stronger ENSO forcing would produce a stronger atmospheric response along the same general lines as the current response. That could mean several things. It could mean stronger outbreaks, with more tornadoes per event and more violent tornadoes specifically. It could mean longer pattern persistence, with the severe weather season extending later into the calendar than it typically does. It could mean expanded geographic impact, with the overloaded zone spreading to include more of the northern plains and the upper Midwest, or potentially shifting farther north as the seasonal jet stream retreat progresses into summer. None of these are guaranteed outcomes. The atmosphere is complex, and the exact response to a strengthening El Niño depends on many factors, including how strong the El Niño actually becomes, how quickly it develops, and how it interacts with other ongoing climate signals. But the general direction of the likely response is toward more of what we have been seeing, not toward a moderation of it. The pattern is unlikely to simply fade away. it is more likely to intensify. The Climate Prediction Centre's forecasts support this general expectation. Current probabilistic forecasts put the likelihood of full El Niño conditions developing by later this year at around 61 to 70%, depending on the specific outlook window and the analysis methodology. That is a clear majority expectation. The Pacific is expected to continue warming, the atmospheric response is expected to continue developing, and the severe weather pattern that is already visible is expected to continue and likely strengthen. And there is another possibility that is worth mentioning, even though it is lower probability. Some analyses put the probability of a so-called super El Niño, meaning an El Niño of unusually high intensity, at around 25%. A super El Niño would be the kind of event that forces the atmosphere into an extreme version of the patterns we've been discussing. It would not be the most likely outcome, but it is a plausible outcome, and it is one that would have significant consequences for severe weather across the United States and for climate patterns globally. This is not a guarantee. Let me be very clear about that. The Climate Prediction Center is not saying that a super El Niño is coming. They are saying it is a plausible scenario with meaningful probability, and probability is not prediction. Most likely, what we'll see is a moderate to strong El Niño developing over the coming months, and the severe weather pattern will scale up accordingly. But the super El Niño tail risk is real, and it is part of why the 2026 season is being watched so carefully. The current pattern could intensify. That is the bottom line, and if it does, the rest of this spring and the summer that follows could be a very different kind of experience for the parts of the country that are already getting hammered. More outbreaks, more compound events, more reload cycles, potentially farther-reaching geographic impact as the pattern shifts with the seasonal jet stream retreat. In that sense, what we have been watching this April, intense as it has been, may turn out to be a preview rather than the peak. The peak, if El Niño develops as expected, may be something we have not yet experienced this season. And that is a sobering thing to say out loud, but it is what the science is pointing to, and pretending otherwise would be a disservice to the people who need to prepare for what might be coming. This is not doomsaying. This is honest reading of the best available climate science in light of the best available oceanic and atmospheric data. The 2026 season is tracking a predicted pattern with unusual clarity. The driver of that pattern is strengthening. The pattern itself is therefore likely to strengthen along with it. And the implications of that for the people in the path are worth taking seriously. Part 17. The Compound Event Era. And there is a broader context for all of this that I want to put on the table, even though it is a secondary topic in this specific story. Over the past several years, climate research, including assessments from the Intergovernmental Panel on Climate Change, has increasingly focused on a concept called compound events. Compound events are situations where multiple hazards co-occur in the same place and time, or in connected places and times, producing impacts that are greater than the sum of their parts. The quad hazard event we have been discussing for April 23rd is, in this technical sense, a textbook example of a compound event. The climate science literature has been documenting an increase in the frequency and intensity of compound events over recent decades, driven by a variety of factors including changes in atmospheric circulation, increases in available moisture and energy, and shifts in the distribution of extreme weather ingredients. Specifically, there has been documented growth in environments that support high, convective available potential energy combined with strong wind shear, which are the ingredients that produce severe thunderstorms and tornadoes. This trend is one of the signals that climate scientists point to when they discuss how the changing climate is affecting severe weather, even if the specific relationship between climate change and tornado counts remains an active area of research without definitive conclusions. What this means, in the context of the 2026 season, is that the ENSO pattern we have been analysing is not operating in isolation. It is operating on top of a baseline that has been shifting over time, a baseline in which the ingredients for severe weather are, on average, more abundant than they used to be. So when an ENSO pattern assembles those ingredients in a particular geographic configuration, the severity of the resulting events can be amplified by the underlying changes in the baseline environment. This is why I want to connect this back to the central thread. The 2026 pattern is not just ENSO operating in a vacuum, it is ENSO operating on a baseline that has been shifting. The same ENSO signal that would have produced a certain pattern 30 years ago is now producing a pattern on top of an environment with somewhat more available energy, somewhat more moisture, and somewhat more shear in many regions. Which means the ENSO pattern, when it assembles, can produce events that are more intense or more impactful than the same pattern would have produced in decades past. Compound events are becoming more common. This is what the research suggests, and the April 23rd Quad Hazard event is consistent with that trend. The implication is not that compound events are unprecedented in an absolute sense. The implication is that they are trending in a direction where we should expect to see more of them, and the 2026 season, with its repeated compound event reloads, is one window into what that future might look like, and that is part of why watching this season matters beyond just the immediate impacts. 2026 is a case study in what happens when a specific climate driver, in this case ENSO, operates on a baseline that has been evolving over decades. It is a case study in how compound events can emerge from the interaction of multiple climate signals operating at different timescales, and it is a case study in how predictive climate science is catching up to the complexity of the real atmosphere. Part 18. The Forecasting Blind Spot. I want to address a subtle but important limitation of the forecasting world that is relevant to what we have been discussing, because it matters for how we should think about seasons like 2026. Forecast models are very good at certain things, and they are not as good at other things, and understanding the distinction is important for interpreting what we are seeing and for thinking about what we might be missing. Short-term storm prediction is one of the great success stories of modern meteorology. Models like the High-Resolution Rapid Refresh and the North American Mesoscale model, along with a variety of others, have reached a level of skill over the past decade or two that would have seemed almost impossible to forecasters from a generation ago. A severe weather outbreak can now be anticipated days in advance with remarkable specificity, and the hour-by-hour evolution can be tracked in near real time with radar and mesoscale models. The warning systems that contributed to the low casualty count on April 17th are a direct product of this forecasting progress, and that progress represents an enormous amount of scientific and technological investment over many decades. Regime shifts and large-scale pattern recognition are areas where our models are still developing. The same models that can nail a tornado outbreak 4 days out may not be as skilled at anticipating multi-month regime shifts or at capturing the full implications of a strengthening ENSO signal for severe weather geography. That is not a criticism of the models. It is a recognition of where the science is right now. The forecasting tools have been optimized for certain kinds of predictions, and the structural pattern recognition gap is an area where there is still meaningful room for improvement. This creates what you might call a blind spot. A forecaster can accurately predict what is going to happen on Thursday, with high confidence and specificity. But getting a clear read on what the entire spring is going to look like based on the regime the atmosphere is in requires a different kind of analysis. And that analysis is harder to do with the same level of confidence. It is possible, and the Columbia team's work is one example of how it can be done, but it is not where the bulk of operational forecasting effort is focused. And this means that the structural pattern we have been identifying in 2026, the way it is tracking a specific climate-driven regime, may be something that does not show up cleanly in the traditional forecasting framework. The individual events are being forecast well. The larger pattern they are part of is more visible to researchers working on ENSO and severe weather teleconnections than it is to the day-to-day operational forecasting community. That does not mean the operational community is missing it, to be clear. Many forecasters are very aware of the ENSO context, but the emphasis in operational forecasting is appropriately on the near-term specifics, and the larger regime question tends to be discussed more in the climate prediction and research communities. The science may be lagging behind system-level changes, in the sense that our tools for recognizing and responding to regime shifts in real time are still developing. We have the theoretical frameworks, we have studies like the Columbia paper, but integrating those frameworks into operational forecasting and into public-facing weather communication is a process that is still underway. And when a season like 2026 emerges, with a pattern this cleanly tracking a predicted regime, it offers an opportunity to test and improve that integration. Are we underestimating pattern persistence? That is a question worth asking. Not because we know the answer is yes, but because the answer matters. If the 2026 pattern is as persistent as the theoretical framework suggests it should be, and if our operational sense of when it might weaken is calibrated to chaotic atmospheric expectations rather than to structured regime expectations, we might be caught off guard by how long the pattern continues and how far into the season it extends. That is a possibility worth keeping in mind as the spring progresses, and all of this loops back to the central thread. The 2026 pattern is structured, driven by a specific climate signal, and behaving with unusual clarity. The forecasting community is watching the events. The research community is watching the pattern. And the interaction between these two perspectives is one of the most important conversations in weather and climate science right now, because it will shape how we prepare for seasons like this one in the years to come. Part 19. The theories people will jump to. Whenever a weather pattern gets this clean, this predictable, this unusual looking in its coordination, a certain set of theories start circulating. I'm going to mention them briefly, because they are part of the cultural response to events like this, and because addressing them directly is more useful than pretending they do not exist. You have probably already seen some of these theories in your social media feeds, especially in the days following the April 17th outbreak. They show up in the comment sections of weather videos. They get posted alongside radar images with captions implying that somebody is steering the storms, and I understand why. When something looks too coordinated to be natural, the mind reaches for an explanation that matches the feeling, and a natural explanation often does not match the feeling, even when it is correct. The theories tend to include references to the High-Frequency Active Auroral Research Program, known as HAARP, which is a research facility in Alaska that studies the ionosphere. They include references to cloud seeding, which is a real weather modification technique used in limited contexts for things like enhancing snowfall over mountain watersheds. And they sometimes include references to directed energy weapons or other exotic technologies that would supposedly be capable of producing or steering severe weather. These theories tend to gain traction whenever a weather event feels unusual or unnatural, and the 2026 season, with its clean structure, is exactly the kind of event that attracts them. The clean cadence, the geographic targeting, the compound events that seem almost staged in their multi-hazard presentation, all of it invites the kind of pattern matching that looks at a coordinated system and assumes a coordinator. These explanations fail physically for reasons that are worth stating plainly, and I want to walk through them carefully, because the physics here is not a matter of opinion. The energy scale of severe weather systems is astronomically larger than anything any known technology can meaningfully influence. A single thunderstorm releases energy on the order of tens of thousands of hydrogen bombs. Let that number sit for a second. One storm, not an outbreak, one storm, and a multi-state severe weather outbreak releases energy many orders of magnitude larger than that. We're talking about numbers that do not have useful analogies in everyday experience, because nothing in everyday experience operates at that scale. There is no technology on Earth that can input enough energy to steer or produce these systems at the scale we are seeing. Even the largest power plants in the world produce output that is trivially small compared to the energy moving through a single supercell thunderstorm in a single hour. Additionally, the atmospheric layer separation between the ionosphere, where facilities like HAARP operate, and the troposphere, where weather happens, is such that influence between them at weather-relevant scales is not physically plausible. The ionosphere sits roughly between 50 and 600 miles above the Earth's surface. Weather, including every tornado, every thunderstorm, every blizzard, and every hurricane you have ever experienced, happens in the bottom 10 to 15 miles of the atmosphere. These are not adjacent zones that casually interact. They are separated by layers of atmosphere that behave according to different physical rules, with different densities, different temperatures, and different energy flows. The idea that manipulating one could meaningfully reorganize the other at continental scale is not supported by any physics we understand. Cloud seeding, meanwhile, is often cited as if it were a proof of concept for weather control. It is not. Cloud seeding can produce small, localized modifications to precipitation under specific conditions, such as slightly enhancing snowfall over a targeted mountain range when the right kind of clouds are already present. It cannot produce tornadoes. It cannot generate severe weather outbreaks. It cannot reorganize continental-scale severe weather geography. It cannot route a jet stream. It cannot suppress activity in Dixie Alley while simultaneously overloading the plains. It cannot schedule troughs to eject from the Pacific on a 6 to 8 day cadence. The gap between what cloud seeding actually does and what it would need to do to produce the 2026 pattern is so vast that the comparison does not hold up under even the most casual examination. And I understand the frustration that leads people to these theories, Look, I am a guy who makes videos about fringe topics from time to time. I am not somebody who reflexively dismisses unusual ideas. I take them seriously enough to actually look at the physics, and when the physics does not support them, I say so. And in this case, the physics does not support them, not even a little. The exotic explanations fail on energy budgets, on atmospheric layer separation, on geographic scale, on the specific mechanisms that would be required to produce the observed patterns. They are not close to being right. They are orders of magnitude away from being right. These theories persist because the pattern feels unnatural when you look at it, and the human mind often reaches for exotic explanations when natural ones feel inadequate. There is a well-documented tendency in human cognition to prefer intentional explanations over coincidental ones, especially when the phenomenon in question is large, frightening, or personally consequential. A coordinated pattern of destructive weather meets all three of those criteria. It feels like somebody must be behind it, because the alternative, which is that the Earth's climate system is capable of this level of coordination entirely on its own, is in some ways more unsettling than the exotic alternative. At least a villain with a machine is comprehensible. An ocean basin silently reorganizing the continent's weather is, in a certain sense, much harder to wrap your head around. But the natural explanation in this case is actually stronger than any of the exotic alternatives. The natural explanation, which is the ENSO-driven atmospheric regime we have been tracing throughout this video, accounts for the pattern's structure, its cadence, its geographic redistribution, its compound events, its statistical anomalies, and its alignment with peer-reviewed science. It accounts for all of it in a coherent, testable framework that has been validated across many decades of data. Not a piece of it, all of it. Every observation we have discussed, from the April 17th outbreak to the Dixie Alley silence to the quad hazard reload on April 23rd, fits inside the ENSO framework without stretching. The framework was there before the season started. The season is now confirming the framework. That is what scientific validation looks like, and it is a considerably higher bar than any of the exotic alternatives can clear. The real cause is the ENSO-driven structure we have been tracing. That is not a speculation. That is what the climate science community has established, and what the 2026 season is currently confirming in real time. And I want you to notice how different this explanation feels from the exotic ones. The ENSO explanation does not require secret facilities. It does not require classified technology. It does not require a coordinated human conspiracy. It requires the Pacific Ocean, which is right there, publicly monitored by satellites and buoys and research vessels from multiple countries, behaving in a way that has been documented for decades and predicted in peer-reviewed literature. Everything is out in the open. The data is public. The mechanism is published. The observations are verifiable. The pattern feels unusual because it is unusual, in the sense that a season this cleanly tracking a specific climate regime is rare. But rare is not the same as unnatural. The atmosphere is capable of producing patterns of great clarity when the forcing is strong enough to suppress the usual noise, and that is what is happening right now. The Pacific is shouting, the atmosphere is listening, and the result is a season that, for once, matches the theory with minimal static. That clarity is what makes the season feel staged. It is not staged. It is just a rare window into what the climate system looks like when one of its major drivers is operating at high volume. So when you see these theories circulating, and you will because the 2026 season is exactly the kind of pattern that attracts them, remember what you have just learned. The physics does not support them. The mechanisms do not hold up. The exotic explanations fail at every scale you examine them, while the natural explanation, the ENSO regime, holds up at every scale and accounts for every observation we have made. That is not a coincidence. That is what a correct scientific explanation looks like. And understanding the difference is part of what separates the viewer who sees the pattern clearly from the viewer who gets lost in the noise around it. Part 20. The closing realization. Let me bring us back to where we started, because the point of this video is not to dwell on what is wrong, but to help you see what is actually happening and what it implies. April 17th was not an anomaly. It was an instance of a pattern. 54 tornado reports, 2 EF3s in Wisconsin, 750 severe weather reports across a single day. All of it was not the atmosphere throwing dice. It was the atmosphere reading from a script a script that was handed to it by the state of the Pacific Ocean, a script that follows rules that have been documented and published for more than a decade, a script that is still being read in real time, chapter by chapter, across the American sky. And I want you to sit with that framing for a moment, because it is the framing that changes how you experience the rest of this spring. Once you see the script, you cannot unsee it. Every severe weather day from here forward is going to look different to you. You will notice the cadence. You will notice the geography. You will notice the silence where silence is not supposed to be. And you will notice that what looks like chaos on the surface is, underneath, one of the most structured severe weather seasons the central United States has experienced in recent years. The shock of the events does not go away, but the surprise does. And replacing surprise with pattern recognition is one of the most useful things a viewer can do going into the rest of this year. April 23rd is not a surprise, it is a confirmation. The same configuration that produced April 17th is producing April 23rd. The same engine, the same ingredients, the same geographic targeting. The quad hazard event that is assembling right now is not an exotic coincidence. It is what happens when a deep trough and a strong surface low interact with Gulf moisture and cold continental air in the specific way that the current jet stream configuration dictates. It is one more iteration of the pattern we have been tracing, and it will not be the last. Not this week, not this month, not for as long as the forcing behind it stays in place. The machinery is still running, and the machinery is scheduled for a lot more output before it takes a break. The Dixie Alley silence is not an absence, it is a redistribution. The energy that would normally be driving late-night tornado outbreaks across Mississippi and Alabama this time of year is not missing from the system. It is simply not assembling in that region because the ENSO-driven jet stream configuration is routing it farther north and west. That redistribution is the other half of the plane's overload. They are not separate phenomena. They are two symptoms of a single underlying condition, and the condition is the ENSO regime that is taking shape in the Pacific. The loud region and the quiet region are telling you the same story, from opposite ends of the same map, in two different languages that turn out to be dialects of the same tongue. And science predicted this configuration. In 2015, a team at Columbia University published a peer-reviewed study that described quantitatively how ENSO would modulate the geography of severe weather in the United States. The pattern they described is the pattern we are watching unfold this spring. The plains and Midwest overload, the southeast suppression, the coordinated cadence, the intense outbreaks. All of it was on paper years before it was on radar, and that is a remarkable validation of climate science. It is also a reminder that when researchers tell us something is going to happen under certain conditions, and then the conditions arrive, and then the thing happens on schedule, we should probably stop treating those researchers as background noise and start treating them as the forward operating scouts they actually are. What we are looking at when we pull back and survey the whole picture is ENSO shaping the geography of severe weather this spring, jet stream configurations enforcing the cadence at which outbreaks occur, and a broader climate baseline that, over the decades, has increased the available ingredients for severe weather in general. These three factors, operating together, produce the 2026 season we are currently living through. None of them is random. None of them is unpredictable in the ways that really matter. The pattern is structured, and the structure is knowable. The structure is also actionable, which is part of why this matters. When you know the structure, you can prepare for it. When you do not know the structure, every outbreak feels like a fresh shock, and every shock is a missed opportunity to have been ready. The pattern is not ending. The Pacific is still trending toward El Niño. The jet stream is still locked into its current configuration. The troughs are still ejecting on schedule. The reloads are still coming. Each iteration of the pattern builds on the last, and the forcing that sustains it is not weakening. If anything, the forcing is strengthening, and the pattern may be evolving toward a more pronounced expression in the weeks and months ahead. The ground across the Midwest is already saturated. The air masses are already loaded. The jet stream is already in place. Every reload arrives with a slight head start compared to the one before it, and that accumulation is part of why this season feels so relentless to the people who are living inside the overloaded zone. And that is where we end, with the question that has been hanging over this entire analysis. What happens when El Niño fully arrives? What happens when the pre-El Niño signal we have been watching becomes a fully developed El Niño signal, and the atmospheric response scales up accordingly? What happens when the rulebook is being read from the full-strength chapter rather than the prologue? Those are questions that the spring and summer of 2026 are about to answer, and the answers will shape how we understand severe weather in a changing climate for years to come. Those answers will come in the form of tornado reports, radar loops, outlook maps, and unfortunately damage assessments. They will come whether we are ready for them or not. The only variable we control is how seriously we take the preview we are already living through. Here is what you should take away from all of this. The atmosphere is not behaving unpredictably this spring. It is behaving exactly as expected, given the conditions in the Pacific Ocean. And the fact that it is behaving exactly as expected following a script that was written in a research journal more than a decade ago is not comforting. It is the warning. Because when the atmosphere follows the script this cleanly, it tells you that the forcing is strong, the pattern is stable, and the trajectory is toward more of the same, not less. Predictability in this context is not a comfort. Predictability is the alarm. We are not in a chaotic season. We are in a structured one. And structured seasons, when the structure is driven by a climate signal that is still building, do not moderate on their own. They continue. They intensify. They write their next chapters in the same handwriting as the chapters before them. April 17th was a chapter. April 23rd is the next chapter. The chapters that follow will be written over the coming weeks and months, and the book they are part of is one we have already read the outline for, in a paper that was published in a time when nobody knew this particular spring would come. That is what makes this moment unusual. Usually we read the weather after it happens. This spring, we have the rare experience of watching weather that was described before it happened, unfolding in the precise sequence the description predicted. The storms that have torn across Wisconsin and Kansas and Oklahoma this April are not the work of an angry atmosphere or a random system or an unnatural cause. They are the work of an atmosphere doing exactly what physics and climate science say it should do under the conditions currently in place. And that is the most sobering thing I can tell you, because it means the pattern will persist as long as the conditions persist, and the conditions are going nowhere but further in the direction that drives this pattern. There is no cavalry coming to break the cycle. The cycle will break when the Pacific tells it to break, and the Pacific is not telling it to break. The Pacific is telling it to amplify. So the next time you see a tornado, warning light up the map across the central United States in the coming weeks, and the next time you see a compound event assembling with hazards that seem to belong to different seasons appearing on the same day, and the next time you notice how quiet the southeast is relative to what it should be, remember what you have learned here. None of it is random, all of it is structured, and the structure is the warning. The structure is what separates this season from a normal one. The structure is what tells us that what comes next is not going to resemble the seasons we have known, and the structure is what gives the informed viewer, the one who paid attention all the way to this point, a genuine advantage over the casual observer who is just watching storm coverage on the evening news. If you live in the plains or the Midwest, take the warnings seriously this season. Every one of them. The system producing these outbreaks is not a one-off. It is going to keep firing. If you live in the southeast and things feel quieter than you're used to, do not mistake the quiet for safety in any long-term sense. The ENSO signal that is routing energy away from your region right now will eventually shift, and when it does, the storms will return. And if you live anywhere else on the map, watching this unfold from a distance, use this season as a case study in what it looks like when a large climate signal takes hold of a continent's weather and refuses to let go. You're seeing in real time something that climate scientists have been describing for years. The atmosphere isn't behaving unpredictably this year. It's behaving exactly as expected. And when a system this vast, this powerful, and this consequential starts behaving exactly as expected, in a direction that points toward more severity, you stop asking whether to take it seriously. You start asking how to prepare for what is still to come. Because the script isn't finished. The Pacific is still warming, the jet stream is still pulsing, and the next chapter, the one we haven't yet read, is being written over our heads right now. It is being written in sea surface temperatures, in Kelvin wave anomalies, in subsurface heat content, in jet stream amplitudes, and in the slow, steady progress of an oceanic signal that has been building for months and shows no sign of slowing down. And when that chapter arrives, the people who understood the earlier chapters will be the ones who saw it coming. The people who dismissed this spring as normal variability, or who convinced themselves that April 17th was a fluke, will be the ones caught off guard. That is the difference that pattern recognition makes. That is the value of climate science working the way it is supposed to work. That is why the quiet southeast matters as much as the loud Midwest. That is why the 6 to 8 day cadence matters as much as the 54 tornado reports. The small details are telling you what the headlines cannot. Stay tuned, stay aware, and stay grounded in the science, because the science is the only thing that can make sense of a sky that, from here on out, is likely to keep giving us more reasons to look up. Watch the outlooks, watch the Pacific, watch the southeast as much as you watch the plains, and remember, when the next outbreak arrives on its scheduled day, that what you are seeing is not weather misbehaving, it is weather behaving exactly as predicted. And a predicted atmosphere, trending in the direction this one is trending, is the single most important thing to keep your eye on for the rest of this year.